So we have an outline of how to approach these problems. The first step is to understand the problem. You got to read the problem. You got to really read it until you understand kind of what's happening. You should be thinking about like what are the unknowns, what are the givens, what are the conditions put upon the problem. The next step would be, after you understand kind of what's going on, is to draw a diagram. For the most part, these problems are going to have like a geometric component to it. So having a picture to visualize is often really helpful. They don't have to have a geometric component. There's plenty of optimization that's like economics based. But often, like, it's a very common presentation to give you like a geometric presentation. When you draw your diagram, you should think about, like what are the variables and what are the givens and what are the things you need to know, and start kind of recording that information in your diagram as you're drawing it. Step 3 would be to introduce notation. So you want to assign a symbol for the quantity that needs to be maximized or minimized. For the sake of their example, they're going to call that Q. And then you want to select some symbols for other unknown quantities and label your diagram. And they suggest using suggestive symbols like A for area or H for height. That's a shocker, right? Step 4 would be to express Q in terms of the other symbols from step 3, i.e. you're going to write an equation. Now, in most of these geometric situations, it'll be like the area of a rectangle or the volume of a sphere or whatever, like some geometric relationship. Step 5 says if Q has been expressed as a function of more than one variable in step 4. So if you're writing an equation for like the area of a rectangle, length times width, 2 different variables, right? So it says then if you have that situation where you have more than one variable, to use the given information to find a relationship among these variables, and use that relationship to eliminate all but one of the variables in the equation for Q. Much like we did in the related rates problem, where we had to find another equation and eliminate a variable. So very similar in that regard. And then use the methods from sections 4.1 and 4.3 to find the absolute maximum or minimum. In particular, if the domain of F is closed, then use the closed interval method in section 4.1. So again, in step 5, it also suggests to write the domain for the function. That's going to be critically important, that you make sure to remember to do that. I know that was in there somewhere, I just forgot to say it. All right, so what do you notice here in terms of new ideas? Nothing, right? No new theorem, no new technique, nothing new. All this is just application of things we've already talked about. It's really an application of finding, a maximum or minimum, right? That's really all we're kind of talking about. All right, so let's start by reading the problem and trying to understand what's going on. A farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? Does everybody understand what we're trying to do? Basically lay out some fencing so that it contains the biggest field possible, right? So here's a sketch. Do I feel good? The blue is the river. Hopefully that was obvious, and the red is the fencing. So let's identify that we're looking to maximize area, right? And let's give some dimensions to this fence here. Since it's a rectangle, the dimensions I would name this should be length and width. Everybody's okay with that? Does it matter which one is length and which one is width? No, right? Could be interchangeable. I chose to name the two sides L and the one side W. Doesn't matter though. Everybody feel so far so good? So if I write my equation then for area, area is length times width. How many variables is area a function of right now? 2. How many do I need it to be a function of? 1. So I need to find a way to eliminate either L or W from this equation. Now there's a piece of information that we haven't used yet. What piece of information is that? Yeah, I have 2,400 feet of fencing, right? So I know that L plus W plus L should equal 2,400. Are you good with that notion there? Now, what assumption did we make? That the biggest possible area will use all of the fencing? I don't think it's a stretch to make that assumption, right? If you're going to look to contain the most stuff, I'm going to use all the fence I have available to contain it. Seems pretty reasonable to me. Everybody okay here? All right. So let's solve this for W, I guess, and then we'll substitute that in. It doesn't really matter, but so far so good. So now I have a function for area in terms of one variable. Before I proceed, I need to compute a domain for this function. So I'm going to ask myself, what's the smallest possible value of L that would still give me a sensible real-world answer? What's that? 0. That's correct. Because 0 times 2,400 minus 2 times 0 is 0. The smallest area that my fence could possibly contain would be 0, because it makes no sense to have negative areas. Is everybody okay with that? What's the biggest possible value for L that my function could contain, or that this could have where the area still makes sense? That's absolutely correct. Yes, good job, Anthony. 1,200. Why 1,200? Yeah, if I plug 1,200 in for L, 2,400 minus 2 times 1,200 is 0. Then that's a 0 area. If it was any bigger than 1,200, though, what would I get? A negative value. Can area be negative? Oh, no, 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 no. So for the most part, you can do this by inspection, like we did here. If you wanted to, you could graph this function and look at what part of this function is above the x-axis, and use your calculator to look at that. That would be fine. That's a little bit of a hassle because the numbers are kind of big, but is everybody good there? Okay. So now we're all the way through step 5, right? So step 6 says use the methods from section 4.1 and 4.3 to find the absolute minima or maxima, whichever is desired here. So notice that the domain here is a closed interval. So I'm going to use the closed interval method. So for the closed interval method, I need to check the value of A at the endpoints of the interval and also the critical values. So we're going to check the endpoints of our interval and the critical values. Everybody's good there? How do I find the critical values? What is a critical value? Or where the derivative does not exist or is undefined. Yeah. So we need to start by taking the derivative of A. Should we do anything to this first before we take the derivative? Yeah, let's distribute that L through, right? Because if we don't, what would we have to do? The product rule. Who's interested in doing that? Not me. I'd rather distribute the L through and then just do it the easy way, right? So the derivative of A should be, good, 2400 minus 4L. So if I set that equal to 0, we get 600. And oops, where does that derivative fail to exist? Nowhere. How do you know that? It's a polynomial. Everybody's okay there? So what do we need to check? We need to check A of 0, A of 600, and A of 1200. And see which one gives us the biggest value. Well, we did those two already, right? When we talked about finding the domain. Guess which one it's going to be? So that's 600 times 1200. It should be 4 zeros, I think. Everybody okay? Though I want to check my directions here because it asks for what are the dimensions of the field, right? So I found the maximum area contained, but what are the dimensions? We know the absolute maximum occurs at L equals 600. How do I find W?
To 720 up.
Just do that, right? That's easy. So there's my answer. It'd be a 600 by 1200 field. And if you had solved for W, you would have gotten the answer for W would have been 1200, and you solved for L, you would have gotten 600. Or if you had relabeled them in a different spot, again, the W could have ended up being the 600 and L could be the 1200 if you'd labeled W as the piece, the two-parter, and L as the one-parter. So just kind of, when we give the dimensions of these things, it's going to matter what your picture was and how you labeled it. It's okay that depending, if you drew two different people, drew two different pictures and labeled them two different ways, get two different answers that are basically like, why are they switched? It's like, well, because you drew the picture with them switched. Let's look at our next example. So it says a cylindrical can is to be made to hold 1 liter of oil. Find the dimensions that will minimize the cost of the metal to manufacture the can. Okay, I want to build a can, cylindrical can, so like a Coke can or something. It's going to hold some oil, and specifically 1 liter of oil. So I don't know, it's going to be like, not huge, like half a 2 liter, right? Find the dimensions that will minimize the cost of metal to manufacture the can. Okay. So let's draw our picture. I think I have a good picture of what's going on. So there's my can. Everybody good there? What are the dimensions for a cylinder that we need to care about? Radius and height. So let's call those R and H. Everybody feel good there? And we're told that the volume is 1 liter. Now, I probably don't want to write this volume as 1 liter. Our textbook tends to be kind of nasty about units. What I probably, because I'm going to ask, it asks for dimensions of the can, and a liter isn't something that's like, has an obvious linear unit parallel to it. My chemistry aces in here. 1 liter is what?
1,000 milliliters.
1,000, well, not, okay, what if we want to use like a cubic unit? What is 1 milliliter? No? I think 1 liter is 1,000 cubic centimeters. I like that because at least it has a length unit in it. Because eventually I have a feeling I'm going to have to make an elimination of variables because my can has a radius and a height in it. I don't want to have a liter in there because how do I convert a liter into a length? Because I'm going to have to do some dividing probably at some point. I don't like that looks of the liter in there. I think that's what it is. Somebody with their phone handy want to Google and just double check and make sure that 1 liter is 1,000 cubic centimeters. I think that's right. I think 1 milliliter is a cubic centimeter. Because if you think about it, a centimeter is just like a little tiny, like a little cube is just basically 1 drop of water. That's like what a milliliter is.
Yeah, it is. Yeah, it is.
I'm good? Okay. One point I knew all these things because I was a professional chemist, but it's been a long time since I was doing that. All right. Everybody's cool with the picture we built so far? All right. What are we looking to minimize? What is the quantity we're looking to minimize?
Like cost of metal.
Yeah, we want it. to minimize the metal we need to manufacture this thing, right? It's not the perimeter, it's the surface area, yeah! Yeah, that's right. Okay, guess what we're gonna do next? We gotta remember the surface area for a cylinder. If I unfold a cylinder, what are the 3 two-dimensional shapes that I get? I get 2 circles and a rectangle. Wonderful. So the area for the 2 circles is just pi r squared, right? One dimension of my rectangle is going to be the height, right? What's the width? It's what? It's the circumference of the circle, right? Because if I think about it, if I cut this and unfold it, this distance here is going to be the distance, was the distance around the top, right? If we cut it and unfold it, that distance was the distance around the top of our can. So the circumference of a circle is 2 pi r. So there's my surface area. Shoot, what do you notice? 2 variables. Wah, wah. All right, so we're going to have to eliminate one of them. What is the other piece that we haven't used yet? The volume, right? What is the equation for volume of a cylinder? Area of the base times the height. What is the shape of the base in this case? Circle. So that should be pi r squared h. Which variable do you suppose we're going to want to eliminate, the h or the r? I would eliminate the h as well, right? I don't want any part of like having to square root anything in here. That looks like a nightmare. Give me that h. So far, so good. And now we'll drop that in, and we'll have surface area in terms of r. What do you notice right away? Some reducing we can do here, right? I'll write it this way. Is everybody okay with what I did there? Why do you suppose I wrote it this way? It's going to be convenient to take the derivative of when it's time to do that. All right, but before we take the derivative, what do we need to do? We need a domain, right? Okay. What do you notice about this domain? What's that? Yeah, it's going to be open, right? Because r can't be 0. We'll just write it this way. Is there a maximum value that r can be? What do you think? If r is like 10,000, is that still going to work? We still get a function, right? or still get a surface area, and it's a reasonable surface area. If R is 10,000, we still get an H. It's a crazy small H. You're basically looking at a pancake, but like your can could be a pancake, or like a puddle of water, really. I mean, that's really the kind of probably the height you'd have, but still it'll work, right? So we have an open interval here. That makes life a little bit trickier. So what are we going to have to do? So I need to check the limit as R approaches the endpoints of SA of R and SA of R critical values. Now, since we're minimizing, what are we hoping is happening at the endpoints? We're hoping it shoots off to positive infinity. That's what we're hoping for. Because if that's the case, then all we have to worry about is which critical value is the smallest. Everybody's okay there? All right. Let's find those critical values first, yeah? So to do that, we need the derivative. What's the derivative of 2 pi r squared? 4 pi r. And what's the derivative of 2,000 r to the negative 1? Yeah, negative 2,000 r to the negative 2. Everybody good there? I did that right? Yeah? Okay. Let's set this equal to 0. We'll do that first. How do I solve this equation for 0? Well, when one is a r with a positive exponent, the other r has a negative exponent. So it's like kind of tricky way of thinking about that. What would be nice is if I didn't have any negative exponents, right? What can I multiply both sides of this equation to get rid of the negative exponent on the r? R squared. Let's do that. That's probably the nicest way of doing this. So 0 times r squared is still 0. R squared times 4 pi r is 4 pi r cubed. And then I have 2,000. So from here I can add the 2,000 over, divide by the 4 pi, and then cube root both sides. And yes, there's some reducing I could do there, but like, I don't really care at this point. Is everybody okay? The unit on that is a centimeter, FYI. So far, so good. Okay. Oops. Okay. And I guess this would be from the right. Everybody agree? Okay. So to do this part, I can just direct substitute this, right? And then if I have the graph of 1 over x, that looks like this, right? Everybody's okay there? So if I have same thing as the graph of like 1 over r, if I'm approaching 0 from the right, oh my goodness, don't do that. I'm looking at this end, right? But I'm multiplying it by a negative. So what's going to happen? It's really going to flip like that. So where are we heading? Negative infinity. Oops. Okay. Oh my God. This is plus. It's plus. I wrote down the wrong thing. How come you guys weren't yelling at me yet? It's plus. Whew. Oh, that is a relief. Okay. I was like, what is going on here? I don't like where this is going at all. All right. So now if we do this one, 2 pi r squared, if I plug infinity in, I get infinity, right? If I have 2 over r and I plug infinity in, I get a constant over infinity is 0, right? And since we're minimizing, we know that the endpoints aren't helping us at all, right? Everybody's so far so good? So the only guy we have to worry about is this critical value. However, we still need to check one thing on that critical value, because we can't just assume that's where the minimum is, because it's possible no minimum exists. What do we still need to check here? That is actually a minimum at that spot, that it's not a maximum there. No, we'll do like a first or second derivative test. We wouldn't want to, I mean, yes, you could graph it, but like, we're trying to use calculus to do this, and like, on the AP exam, these are for sure no calculator questions when you run into stuff like this, where it's like, oh, I could just graph and look at the picture. Like, they will not give it to you in a section where you can do it. So I would probably second derivative test this guy, because I don't want to worry about like what's a value bigger and smaller than this number, because I have no clue what this number even looks like. Everybody's okay with that plan? I mean, I can look at it and sort something out of this, but it's still like pretty sucky. So let's just do a second derivative test, because then we can just plug this same value in and just look at whether we get positive or negative. All right, so if I do that, I get 4 pi r plus 4,000 r to the negative third. Everybody feel good? Oops, I should write it over here too. Now, what do I care about when I plug this in for a second derivative test? I just care about if it's positive or negative. What is that going to come out to be? Positive. How do you know? All the components are positive and you're adding, right? There's nothing else that can happen. It has to be positive. So, therefore, r equal to the cube root. I'm going to reduce this because it's just getting obnoxious. So that's 500 over pi. And it wants the dimension too, right? So I also need height. So for height, I know that that's 100 over r squared, or pi r squared. Or sorry, 1,000. And these units would both be in centimeters. Is everybody okay there? What we did? What was the worst or the most obnoxious part? Having to do these limits at the endpoints to check, right? That stinks. So this little theorem or method will kind of allow us to eliminate having to do those limits. So that's all this is doing, is just a workaround for having to do those limits. So this method says that if the first derivative is greater than 0, for all x less than your critical value, and less than 0 for all x greater than our critical value, then that has an absolute maximum at the critical value. Likewise, if it's reversed, it's an absolute minimum at that critical value. So this is a situation where we have one critical value. This is the method I would want to use. So I'm going to pause here for a minute because I see people writing still, and then we're going to troll back to that first derivative and show you how we could use that to skip having to look at those limits and also do the second derivative test. Right? This will hammer the whole thing out for us pretty nicely. Is everybody okay with that plan? I like that, right? Okay. Am I okay to move? If it's no, say no. Are you still writing? Okay. Just say no. Just be like, I need like 10 more seconds or 20 more seconds. It's not a big deal. I don't want to sit here for nothing, but if you're writing, like, that's a reason to not move. You know? I'll eat a delicious grape and, you know, wet my whistle, so to speak. We ready? Let's do it. All right. So we go back. So stop. There we go. So right after here, where I've found only one possible critical value, I'm just going to pick a test value on either side of this critical value. It's nice because if I look at this number, what is this number clearly bigger than? But I can't plug 0 in, right? Give me something else. 1, right? Should be able to see that because there's 1,000 in this side of this cube root. The cube root of 1,000 is 10. That's going to be 10 times something. As long as that number's, not like a crazy decimal that we're multiplying it by, probably going to be okay. And it is a crazy decimal, right? It'd be 2 over 4 pi, which is about 1 over 6, but that's not less than 10, right? It's like dividing by 6 instead of dividing by 10, so we're still in the clear. It's not too small. 1 will be fine. Is everybody okay with how I kind of like intuited my way through guessing? And then something bigger? What do you think? I don't know. 10, right? A 10 pulls out, we're multiplying it by a number less than 1. So 10 is certainly bigger than that. All right. So if I plug this into the first derivative, if I plug 1 in, 4 pi minus 2,000 is negative. If I plug 10 in, 40 pi minus 200 divided, or 2,000 divided by 100. Positive, right? Since this is true for all values that are less than C and all values greater than C, I can stop. I found an absolute minimum. Notice I didn't have to do a second derivative test here. I didn't have to worry about the limits at the endpoints. That saved a lot of stuff that we did, right? Woo! That's nice. All right, how are you guys feeling here? I know, this is hard. Now my stuff is like all screwy-dooey. Probably have time to do a couple more of these. I have a whole boatload of them, though. Yuckarooskies. Let's see, is there one that's not like super geometric? Let's do this one. I'm going to pick this one because it's not geometric. Let's see if we can remember how to do it. The geometric ones are easy because I can just draw the picture and it's easy for me to walk my way through it. The ones that aren't geometric sometimes are, like the elimination step can sometimes be a little tricky, or how to formulate it. It says a store has been selling 200 Blu-ray disc players a week at $350 each. A market survey indicates that for each $10 rebate offered to buyers, the number of units sold will increase by 20 a week. Find the demand function and the revenue function. How large a rebate function, or how large a rebate should the store offer to maximize its revenue? Probably need to read that again, right?
At least 3 more times.
Yeah, at least. So a store is selling Blu-ray players, and for every $10 discount that's offered, the number sold is going to increase by 20. Find the demand function, so that's going to be like how many players we're selling. And the revenue function, that's going to be how much money is being brought in. And we want to find how large a rebate, so it should be $10 or $20 or $30 or something else, to maximize the revenue. So there's no picture to draw here, right? Does everybody kind of get a feel for what's going on? All right. I'm going to say let so I'm going to define X to just be one Blu-ray disc player. And we're going to say d of x is our demand function. We're told d of 200 so d of x should be I don't want X to be Blu-ray disc player. So my demand function should be 200 plus X, or sorry, 20X. Right, and X is going to be like the number of $10 rebates offered. That makes sense to you guys? And then my revenue is going to be 350 times that demand function. Not quite. Because we're not charging 350, we're charging 350 minus 10x, right? That's what we're doing. Does that look right to you guys? Okay. My domain for x is going to be 0 to 350, right? Oh, I'm sorry. 35. Sorry. So in x is 0, that's no rebate offered, right? When x is 35, that's a $350 rebate. That's the entire price of the unit. We're giving them away. Pretty sure that's not going to be the answer. Is everybody good with the reasoning there? What I like about this is closed interval, so I know exactly what to do, right? All right. Probably going to start by foiling this out, right? I don't want to product rule this if I don't have to. So what do I get? I get 70000, I think, plus 700x minus 2000x minus 20x squared. Is that 70,000? 300 times, yeah, that's gotta be right. Okay, or just 70,000 minus 1300x minus 20x squared. I'll find my critical values. I'll set that equal to 0. And set it not equal to 0, or I'm sorry, to not, or to does not exist, but there's none of those because it's polynomial. So that's nice. I just need to now solve this quadratic, right? How would we want to do that? Yeah, let's divide by -20 to start, right?
That's 650. Oops. X.
Anybody see how to factor that? Multiplies to give us negative 3,500 and adds to give us 650. $750 multiplied to give us 3,500, right? So positive 700 and negative 50. I think. I feel like I've goofed on a decimal point somewhere here. What's that?
Would it just be 70?
70?
Yeah.
Oh, yeah. That's not going to do it then. Thank you. It's like those numbers made no sense for those being my critical values. I don't know, quadratic formula this thing? I've looked at it long enough. I don't want to do it anymore. So negative 650 plus square root 650 squared minus 4 times 1 times negative 3,500 divided by 2. So those are the results I get. Now this one is bonkers. Why can I eliminate that one immediately? It's outside of the domain, right? Like crazy answer, that ain't gonna do it. So now we just check. So I'm gonna do R of 0, R of 5.34, and R of 35. Now, I know that this is 0, right? If I'm charging $0 for my DVD players, I'm not making any money at all. It's a bad deal. If I do 0, I get 350 times 200. That's 70,000, I think. And then if I plug in 3 or 5.3, it's a lot of discounts. All right, let's type this thing in because I'm not doing this in my head right now. And I'm not totally sure I didn't make a boo-boo like foiling this out or something. That's a weird number, but maybe it's just like it's a weird number, you know? And I get 90,996. Oh, and 88 cents. So how large a rebate? So my rebate is going to be 10 times 5.34 or $53.40, thereabouts. It's a big discount. Is everybody okay there? So again, here's an example of a problem that involved no geometry to speak of. Business or economics is a very common type of optimization problem though. Because oftentimes when you're running a business, what are you looking for? Maximize that profit, you know, like I want to make the most stuff I can possibly make. Let's stop here. This feels like a good stopping point, right? You guys seem like you're kind of cooked at this point, which is okay. Next class, we're just going to do some practice in class. I'm going to give you guys some stuff to work on. Basically, I will give you some practice problems involving related rates or these first, second derivative tests or optimization, and just let you guys do some practice in class, ask some questions, work together, and try to get a little bit better at this stuff. Because these are exactly the types of questions you're going to see on the final in the application section, are these types of questions. So, might as well do some practice and start getting good at them, because you have to do some of these things. Okie dokes. Also, it should point out that I made a related rates delta math before Thanksgiving break. If you're interested in doing some practice there, you're like, yo, that's a skill I stink at. Like, that's a way to get some immediate feedback about whether things are going right and wrong. That's there, it's optional for you. So you can practice or not, but that's there. Okie dokes. How you guys feeling? How's your end of your semester looking? Alice is like, I want to say, but I shouldn't because it's really mean. What's the scariest end of the semester? This final? That's okay, you can say that.
Yeah, bio.
Bio is scarier? If you can just borrow her glasses.
I'm bored now. Yeah.